Good morning, students. Good morning, students. In the last classes, we have discussed about different types of filters. In that, we have discussed about the low pass filter as well as high pass filter, and using these two filters, how to obtain a band pass filter we have observed, and also different order of filters we have observed, that is first order filter and its response, second order filter and its response, higher order filters. How to construct the higher order filters also we have observed. And now in this class we are going to discuss about band reject filter. So the band reject filter, which is also called as band stop filter. That means whatever the band, that is the frequency band, we are going to select, that will be not allowed by this filter. The band which we have selected will not be allowed by this filter. So this filter is called as band reject filter. For that reason, this filter is named as the band reject filter. And it is also called as band elimination filter. So this is further divided into two types. That is a band pass filter and as well as band stop filter. Sorry, narrow band reject filter as well as wide band reject filter. So narrow band means, as we have seen in case of band pass filter, so the bandwidth will be a narrower, and wide band reject filter means the bandwidth will be wide. The bandwidth of the filter will be wide. So first we are going to see the response of narrow band reject filter. So when coming to this narrow band reject filter, so this narrow band reject filter is also called as notch filter. So which rejects, this notch filter rejects a single frequency. So for example, if you take a signal, so if the signal is affected by the power signals. So for every systems we are using power. So the power is also having the frequency, which is a constant frequency. So we know that the power frequency is around 50 hertz. So such type of power frequencies will also affect the communication channel. So that is communication frequencies. So if you want to reject only the power frequency, that is, which is about 50 hertz, that is the 50 hertz frequency, will be rejected by our notch filter or narrow band reject filter. So in such cases, we are going to use this notch filter. So to obtain this notch filter, so we are using a band pass filter. And the screen, you can observe a band pass filter and a subtractor. A band pass filter and a subtractor will be forming a notch filter. So as we know that the band pass filter which we have given, for which we have given input to inverted terminal of op-amp. So the output will be inverted. This inverted output, which is nothing but a negative. Inverted output means the output will be a negative. So this will be given to a subtractor, and then we are going to obtain a notch filter. We are going to obtain a notch filter. So as we know that, so to form a notch filter, we have discussed that the simple technique is we have to use a band pass filter and a subtractor. So when we are using band pass filter using an operational amplifier, so then it is going to produce a negative output. So when it is producing a negative output, here instead of using a subtractor, so as the output of this band pass filter is negative when we are going to use an op-amp, so instead of using a subtractor, we are using a summer. So that is adder. So here you can observe it. So here we are using a second order band pass filter and an adder. So this band pass filter, which has a gain of A0, so that the output at the center frequency will be minus A0 into Vi. The output at the center frequency will be minus A0 into Vi. To completely subtract this output, the input of the summer must be A0 into Vi. A0 into Vi. Thus, the gain A0 must be added between the input signal and the summer. So, A0 will be added between the input signal and the summer. Then the output of the circuit will be so V0 of S. So the output of the circuit will be, here you can see, V0 of S is equal to A0 Vi of S plus A0 into Vi of S plus the gain of the band pass filter. The gain of the band pass filter. So when we solve this, you can observe we are going to obtain A0 into S square plus omega naught square divided by S square plus alpha omega naught into S plus omega naught square. So this is not nothing but the transfer function of second order notch filter. Why we are using here second order band pass filter? So this is the transfer function of second order notch filter. So if you observe a circuit diagram, so if you observe this circuit diagram, the circuit diagram will be like this. So here you can see this is a band pass filter and this is a summer. Band pass filter and adder. So which is going to act like a narrow band reject filter. So which we are calling it as notch filter also. So this is one type of the technique for implementing a notch filter. And another technique is using twin T network. Using twin T network, we are going to implement a notch filter. So that is what we are going to see now. So using a 20 network. So this is a 20 network notch filter. This is a 20 network notch filter, in which the quality factor and bandwidth will be given by if you are going to write here, you can observe. So different nodes. Here you can observe different nodes. So for obtaining the gain, that is the transfer function of this filter, notch filter. So we are going to write KCL at node A, or this is called node A, and we are going to write a KCL at node B, and as well as we are going to write the KCL at node P also. So at these three nodes, you can go A, B, and P. So at these three nodes, we are going to write the KCL, Kirchhoff's current law. So we are going to obtain the three equations. We are going to obtain the three equations. From those three equations, we are going to obtain the transfer function of this notch filter. Obtain the transfer function of this twin T type notch filter. Twin T type notch filter. So let us see the equation at node A. At node A, so we are going to obtain VI minus VA KCL. If you are writing KCL, so the input is VI minus VA into, so we are going to write in frequency domain this into SC. So as we are going to write in frequency domain, so we are going to place capacitor as smallest into C plus. So this is completed, and next plus V0 minus VA into SC. V0 minus VA into SC. So why we are writing V0? So why? Because so as this op-amp A1 is going to act as a voltage follower. Voltage follower means, so we know that due to virtual ground concept, as we have discussed in the last classes, so whatever the voltage at this node will be equal to the voltage at this node also. That means voltage at inverting terminal is equal to the voltage at non-inverting terminal. From that, we can write voltage at this node is nothing but V0, because V0 is fed back to the inverting terminal. Then here also we can write V0. So V naught minus VA into SC. So that is how we have written this equation. Plus, and again, this path is completed and this path is completed. Plus, next we are going to write here we are going to consider the path that is R, R2, R1 and R2, R1 and R2. So we are going to write we are going to take a constant value that is R1, R2. So we are going to write in this path. Now the left path is this path. So for writing that, because the voltage at this node will be going to depend upon R1 and R2 values also. So we are going to take a constant value such that, so we are going to write take that constant value as K, and K is equal to, so nothing but K is equal to R2 divided by R1 plus R2. And conductance G is equal to 1 by R. So here the path is, in this path the resistance R is also there. So for that reason we are going to consider R, and we are going to consider it as conductance, as we know that the reciprocal of resistance is nothing but conductance. So it will be written as V, G is equal to 1 by R. So using these two, we are going to write the equation, that is the output will be the K factor, the factor K, which is equal to R2 by R1 plus R2 into this voltage. So K into V naught, K into V naught minus, so this voltage will be obtained at this node also, because as it is A2 is a voltage follower. So K into V naught minus, so here at this point the node is VA, K into V naught minus VA into, so as we have considered R is equal to 1 by G, or G is equal to 1 by R, so R by 2 is equal to 2G. So in this part we are having R by 2. So we have written the equation like this. So finally we are having three paths from node A. We are going to write KCL at node A. So this is one path, and this is another path, and this is the another path. So for these three paths we are going to write the equation. So for this path we have obtained VI minus VA into SC plus V naught, that is this V naught minus VA into SC, and coming to this path K into V naught, as we have discussed it, the voltage of this node is equal to the voltage of this node. So at this node the voltage will be K into V naught. So K into V naught, and this part we are having resistance R by 2. So we are going to consider R is equal to 1 by G, and then R by 2 will become 2G. So R here, in place of R we are going to write 2G. So K into V naught minus VA divided by 2G. So divided by naught into 2G is equal to 0. So by solving this equation we are going to get a small equation, and then similarly at node B also we are going to write the KCL, and at node P also we are going to write the KCL. So when we are considering at node B, VI minus VI minus VB into G, because the resistance is in this part, plus V naught minus VB into Z again, plus another part is, so this part. So 2 into KV naught, because here it will be KV naught minus VB into 2SC, nothing but 2SC. Okay, KV naught minus VB into 2SC. Okay, which is equal to 0. This is at node B. And coming at node P, so the equation will be, so how many parts are there at node P? So again, we are having V naught, VA minus V naught, and this part, this is another part, and this is another part, and this is another part. Okay, so in this part, we are having VA minus V naught into SEC, plus in this part of VB minus V naught into Z, because here we are having R. In the place of R, we are going to write it as V. So 1 by R, we are going to write it as Z. There is the R, we are going to get, then we are going to write it as Z into Z. So which is equal to 0. So by solving these three equations, so we are going to get a transfer function V naught by Vi is equal to G square plus SC square divided by G square plus S square C square plus 4 into 1 minus K into SCG. Then we are bringing this equation in this form. So S square plus S plus the constant square, S square plus S plus the constant square. So after writing this equation, so we are going to place S is equal to J omega. In the place of S, we are going to replace with J omega. So then the transfer function H of J omega is equal to omega square minus omega naught square. So as omega naught is equal to G by C, as omega naught is equal to G by C. So we are going to write it as omega naught square minus omega naught square minus J4 into 1 minus K omega naught. So F naught is equal to 1 by 2 pi r. So from this, so we are going to obtain the higher order frequency as well as a lower order frequency, that is a lower frequency as well as higher frequency, that is cutoff frequencies, and the bandwidth, which is nothing but the higher frequency minus the lower frequency. So we are going to obtain the bandwidth, and then the quality factor, which is the ratio of the center frequency to the bandwidth. This is the ratio of the center frequency to the bandwidth. So in this way, we are going to obtain a notch filter which is having a narrow bandwidth. So which is having a narrow bandwidth. So by adjusting, so as we know that the quality factor and the bandwidth is going to depend upon, so here you can see the bandwidth is going to depend upon K and F naught. So as we are going to vary K, we are going to vary K. If we vary this K, if we change this K value, so then we can change the bandwidth. So then we can change the bandwidth. As we know that the K is equal to R2 divided by R1 plus R2. R2 divided by R1 plus R2. So by changing this value, so we can change the bandwidth of, so here you can see we can change the bandwidth of the notch filter, and also the quality factor, and also quality factor can be changed. So this is how we are going to obtain the notch filter by using two methods, that is narrow band reject filter. That is, one method is by using a band pass filter and an adder, and another method is by using twin network. Twin network, that means nothing but two T networks. By using the two T networks, we are going to obtain this narrow band reject filter or a notch filter. And coming to the next concept, wide band reject filter. So wide band reject filter. So this wide band reject filter, so coming to this wide band reject filter, you can see by using simply a low pass filter and a high pass filter and an adder. By using a low pass filter and high pass filter and an adder. So you know that this is the response of low pass filter and this is the response of high pass filter, and if we combine these two responses by using an adder, then we can get the wide band reject filter. The wide band reject filter, in which the low pass filter is giving the higher cutoff frequency, that is FH will be given by the low pass filter and FL will be given by the high pass filter, and by combining these two filters response using an adder, we are going to obtain a wide band reject filter. A wide band reject filter. Simply we can obtain this wide band reject filter. So here a problem has been discussed. Design a wide band reject filter in which he has given that FH is equal to 400 hertz and FL is equal to 2 kHz, having pass band gain as 2 and the pass band gain as 2. So for high pass filter, so FL is equal to 2 kHz and which is equal to 1 by 2 pi R2C2. That is, we know that the cutoff frequency for y is equal to 1 by 2 pi RC. So as R and C values are R2 and C2. So in this we are going to assume the C2 value and we are going to obtain R value with the help of given frequency. With the help of given frequency, then when we are going to find this frequency, when we are going to find this R value, so it is around, we are going to obtain it's around 795 ohms. So we are going to approximate it to 800 ohms and we are going to replace it here. So design means we are with the help of the given values, we are going to obtain the values of the passive components in that circuit. So we have obtained the value of R value, that is 800 ohms, and we have assumed that C2 value was 0.1 microfarad. We are going to place that here, and then what will be the R1 and RF value? So as we have given the pass band gain is 2. So here it is an inverting amplifier. So non-inverting amplifier, because the input which we are giving to the non-inverting terminal, as we know it, the gain of non-inverting amplifier is 1 plus RF by R1. So here RF is the feedback resistance, R1 is the RI resistance. So 1 plus RF by R1 is equal to the gain is given 2. So 2 is equal to 1 plus RF by R1. Then so if we see this equation, then we have to come into notification that RF must be equal to RI. Because when RF is equal to RI, then the ratio of this value will be equal to 1, and then 1 plus 1 is equal to 2. So simply when RF by RI is equal to 1, that means RF is equal to RI. So let us consider this RF and RI value as 10 kilo ohms. So why we have taken only 10 kilo ohms? We will choose 1 kilo ohm. So because, so as the resistance we are choosing here, R2, which is around 800 ohms, which is nearer to the value of 1 kilo ohms, that is 1000 ohms. So the RF value must be 10 times greater than this input resistance value, whatever the resistance we are going to use. So for that reason, we are going to use the RF as for maintaining, this is for maintaining stability for an operational amplifier. So for that reason, we are going to take this RF value as 10K, and as the passband gain is given 2, then RF is equal to R1. So both are taken as 10 kilo ohms. Similarly, for the low pass filter also, we are going to consider R1 and RF value of 10 kilo ohms. And according to the given frequency value of the low pass filter, so we are going to obtain the values of R1 and C1. So we are going to assume C1 value, and we are going to find the R1 value. So here R1 value, what we have got is the 4 kilo ohms. So this is the value we have got, and it is nearer to 4 kilo ohms. We are going to replace it with 4 kilo ohms, and we are going to place in these values. When a design problem is given, then we have to draw the diagram, and after that, whatever the values we have found, that values must be written in the circuit, and then only the design problem will be completed. So with that, we are going to obtain all the values, all the passive component values with the given values. This is how the design of band reject filter, that is wide band reject filter, using operational amplifier. And the last concept is nothing but all pass filter. So that is all pass filter. This is the all pass filter. That means this filter passes all frequency components of the input signal without any attenuation. So without providing any attenuation, this filter is allowing all the frequencies, and it also provides a phase shift at different frequencies of the input signal. It also provides the phase shift of different frequencies of the input signal. When the signals are transmitted over transmission lines, such as telephone waves, then the signal will undergo a phase change. These phase changes can be compensated, but these can be altered by using all-pass filter. So where we are using this all-pass filter? In case of telephone lines, so the phase changes of the signals may occur. That changes can be compensated, that is, can be altered by using this all-pass filter. There, we are going to use this all-pass filter. So, this all-pass filter is also called as delay equalizers. Delay equalizers or phase correctors. So, as it is adjusting the phase of the signals, these are also called as phase correctors. So here in the circuit we can see the all-pass filter and which RF is equal to R1, in which RF is equal to R1. So for obtaining the output voltage, so V0 is equal to RF by R1 into VI, RF by R1 into VI plus 1 plus RF by R1 into VA. So here we are going to give the input signal to the two terminals of op-amp. So we are providing the input signal to non-inverting terminal to R1, as well as we are providing the input signal to non-inverting terminal to R and a capacitor. That is nothing but a low pass circuit. A low pass circuit. So, and we are going to take RL. So the output will be V0 is equal to RF by R1 into VI. So here you can see V0 is equal to RF by R1 into VI plus 1 plus RF by R1 into VA. So VA is nothing but the voltage at node A. So as RF is equal to R1, so this equation becomes V0 is equal to minus VI plus 1 plus 1 becomes 2, 2 into VA. So from this we can write VA is equal to where VA is equal to, so where the VA is given by the capacitance divided by total reactance in this part, nothing but. So that is what we have written here. VA is equal to minus JXC divided by R minus JXC. R minus JXC into VI, input voltage. So by keeping this VA value in this equation, so we are going to solve that equation. So we are going to get V0 by VI is equal to 1 minus 2 pi of C into R divided by 1 plus J 2 pi of C into R. So if you consider the magnitude, so this is how we are going to obtain the magnitude. So we can see it can be, we can observe that V0 is equal to 1 minus 2 pi of RC and VI is equal to 1 plus J 2 pi of RC. Both are equal, but only the change is minus and plus. That is, if you consider the magnitude will be same, but the polarities will be different. That means nothing but the phase shift. That means nothing but the phase shift will be there. That is pi. Phase shift will be there. That is pi phase shift. Pi by 2 phase shift. That is 90 degrees. 90 degrees phase shift will be there, and in such a way, this all-pass filter passes all the signals which provides the same output That means there is no attenuation of the signal. Simply, whatever the input we have given will be produced as output, and there will be a phase shift of 90 degrees. And there will be a phase shift of 90 degrees. So this is about the all pass filter. So with this, we have completed our fourth unit, that is filters. Thank you, students.